All right, we start here. This is the second part of Newton's laws of motion. We're going to look at more examples. I did a few examples last week, but I think it's not enough, so we are going to go through, especially we are looking at some specific force. Now, the first force I want to pay attention is friction. Now, friction is, remember I say there's only 4 fundamental forces: gravitation, electromagnetic, strong nuclear, and weak nuclear. Right? Friction is originally is electromagnetic. It means it's all about bonding. Now let's look at this illustration here. Now when you look at the microscopic, if you really have a microscope, magnify up to about 1,000 times, you see no surface is flat. It means when we say a surface is smooth, it's up to micrometer. Yes, you can produce very good atomically flat surface in a very special circumstances. It only can be done in the laboratory. So you see all the surface have all this gap here. Now if you look at here, a lot of gap here, they're actually, if you magnify, they're still, all right. They're all surface here. Now, if this is an atom, there's another atom, there's a bonding. Now, this bonding itself is electromagnetic. It means bonding is chemical. Chemical is electricity and magnetism, chemical bond. So there's a bonding all between here. So think if you want to move this subject to the right-hand side, what you need to do first. Just like if top and bottom, they're bond. So if you want to move the top of the surface to the right-hand side, what you need to do? Break it, exactly. So you have to break those bonding. Therefore, you need force. You need energy. So if you look at really microscopic friction, it just means breaking the bonding between the two surfaces. Now, when you say, all right, once this one, it was here, once it moved to here relatively. Now, once you move the new position, the bonding will form again. So therefore, you have to keep breaking those bondings. Now, this is the origin of physics. Now, if you look at here, that's why this is important idea. You all know, some of you know, the friction. I mean, if you try to move here, the force, you know the friction, either here is opposite to where you try to move your object. Now, this here, you see it depends on how much bonding formed between the two surfaces. So if you put more force on top, what happens? You get more bonding. Therefore, you need more horizontal force to break it. Therefore, you can see now, I say again, it only depends on the normal force. So therefore, this is we always say the friction here is proportional to the normal force. And this proportional quantity is mu. It depends on the surface properties. All right. So it makes sense now because now you know it is the number of bonding you have to break. The more force, think about it. If you try to move this one here, it's easy. You just push it. If someone say I push a force, what happens? You just can't. But remember, I say in the Newton's law, the direction this force in principle shouldn't be any to do with anything about horizontal, but in friction it does. So the vertical force will affect the horizontal force only in friction, because it increases the number of bonding. So when you try to move it, it's a lot harder. So remember the physics. Therefore, all the formula, all the mathematics flow and follow naturally. It's not something you have to memorize. Now, I want to show you 2 videos which it is a good video, so I always show videos when it's really important. Now the one I want to show is here. All right.
In this clip, we begin our little mini-series on friction. And we're going to study various aspects of friction. But first of all, let's take a look at how we will measure the friction. I'm going to pull a block along the surface with a spring balance at a constant speed. Now watch this very carefully. I will try to make this as steady as possible. Now, if I pull something at constant speed, the forces are balanced. Constant velocity means forces balanced.
All right, remember he said if things move at constant, but you do have a force here. So the only conclusion, now if you apply the first law of motion, if this is constant, the sum of all forces must be 0. But you do apply a force here. Therefore, I remember I said in the last lecture, there's a difference between 0 force and the sum of force 0. It's slightly different. Now we have the second situation. The sum of the force is 0. So it means there's one force here, there must be, you deduce, there must be another force opposite. And this force has to be friction. Now, this friction will be as much the same magnitude, but opposite the direction of the force you apply to here. The same argument, if this one doesn't move, you keep push here, it means if you push 5 Newton, it's still not moving, it means the friction is again 5. Now, look at here how he measure. He measure with the spring balance, try to drag this one along the sort of constant speed. It's a rough measurement, but it does illustrate the physics.
The pull force must equal the friction. This is how we can measure the friction. What we want to do is find out what does friction depend on and what does it not depend on. You might be surprised. So first, I have 4 blocks, and they're all about the same size and the same weight. And with a spring balance, I have found the weight of them. Each one is about 2 newtons. Now what we're going to do is measure the friction pulling 1, and then 2 of them stacked, 3 of them stacked, and then 4 of them stacked. And then we will plot a graph of the friction versus the weight. So let's take the data and plot a graph. It's friction versus weight. There's the data on the right. I suggest you hit pause and try it yourself first. I put 0, 0 as a point. If there's no friction, there's no weight, no friction. And at 2, it's 0.5. And at 4 newtons, it is 1. So we'll put our little dot there. And at 6 newtons, it's 1.5. A little bit, there we go. And now, let's see, 8 is 2. So I'll plot that here. Now it looks certainly like a linear relationship to me. So I will draw the best fit line. So the line of best fit, let's take a look. Right about, I think, here. So we see that in this case, the friction depends on the weight. Now there's more to say. But for now, the friction depends on the weight.
All right, we all accept the more weight, it means the higher the normal force, it depends. Now, how about surface area? Now, this is an interesting question.
Okay, to this point, we found that the friction does depend upon the weight. The more weight that we have pushing down, the greater the friction. Now, that's sort of the truth. There's a bit more to be said, and we'll get to that in a moment. But this question, how does the friction depend upon the area? Here's what I mean. Now, we've already seen what happens if I pull 4 blocks, and we saw that the friction was about 2 newtons. Now, what happens if I double the area but keep the weight the same? Then what happens if I triple the area but notice keep the weight the same? Then I 4 times the area but keep the weight the same. Now, I'd like you to make your best guess. Now, hit pause, get a little piece of paper, and here's what we're asking. If we have double the area but the same weight, what happens to the friction? If we have triple the area but the same weight, what happens to the friction? If we have 4 times the area but the same weight, what happens to the friction? Make a little list, take your best guess.
All right, what's your answer? The same weight? So, somebody say same, Annabelle?
Friction will grow as surface area grows.
Friction will increase when the surface area increases. Any other question? Double it. So you expect now, if you borrow your mobile, just nice similar. Don't worry, I won't drag your mobile. Now the same, the 2 mobile here, you can measure the force, and now you put it here with the friction force, same or double? Because a double area. But think about the origin of the friction. Now let's go back. What's the physics? Let's say that's the physics now come in. For example, if I have a 1 phone here, we have a 10% of chemical bonding. They are bond. So if you push, it means you have to break 10% of chemical bonding. All right, got it. So, but for example, got a 100 atoms in you remember there's a gaps. There's not all the atoms that bond. There's a lot of gap in between. There's only about 10%, but maybe 10 out of 100. When I push this one here, how many atoms here become bonding? From 10 to 20. Because you increase the weight. Make sense? So it means now you have to break how many atoms? 20 atoms. Got it. Remember, you have to break 10 atoms every time you move. Put this one, you have to break 10 atoms. So yes, it makes sense. The more high the mass, the more friction. How many atoms you have to break again? 10. How about put this one here? How many atoms have to break for here? 10. Overall?
20.
So will the friction increase? You still have to break how many bonding? 20. Can you follow the argument? So therefore, you expect, if you know the physics again, now you see you can guess with common sense. It's good. We are all coming from the common sense. But once you learn physics, you're not common sense guessing anymore. You're becoming educated. Well, that's what education means. You're different from the people in the street. Got it? That's why people pay you $100,000 for an engineering job. Otherwise, they will get anybody in the street got the job. Agree? You got the skills. Therefore, now it's your intelligence. Say yes, 10 atoms, 20 atoms. But I can spread this one here, 10 atoms, 10 atoms. So still 20 atoms. So therefore, you expect the friction. Yet it won't affect by the area. It's all about how much weight total weight. You can distribute here, you can distribute here. Make sense? When you distribute here, you just increase the number of bonding from 10 to 20. You spread a little bit 10, but you spread on an over larger area. So a larger area doesn't mean you have a larger friction. Just like if you put it here, thank you. If you put the phone here, 10 atoms. If you do it here, I will say again 10 atoms, all right? Again here, 10, because it only depends on the weight. It doesn't matter how you put your block. So the friction, the multiple choice, one of the multiple choice this week we've asked you if we have a free configuration, 1, 2, 3, for the same object, will the friction change? Yes or no now? No, because the same way you're not getting the physics still. Remember, I say it's the bonding. The bonding, how many chemical bond between the two surfaces depend on what? The weight. So it doesn't matter the area. It will automatically increase the number of bonding, but it will remain the same. All right? So let's see. Now, seeing is really beautiful.
Area, and notice it's very close to 2 newtons. Now we triple the area. Watch the spring balance. Very, very close to 2 newtons with an experimental measure. Now we will quadruple 4 times the area and look very closely at the spring balance. And it's very close to 2 newtons. So were you surprised? It's very surprising, I think, for most people to realize that the sliding friction doesn't depend upon the area that's in contact. When I do this with a large class of students, I'll have 30 students, and almost all the students will guess, oh yes, you double the area, you double the friction, triple it, and 4 times the area.
So if you guess like this, you're not special. If you guess this right because you may already know it, or you have a very good logic.
4 times the friction. And while we're doing the experiments, you can often hear them saying, what's wrong with our lab? Something isn't working. Sir, can you come and help me? This isn't working. And this just goes to show you how important it is to do experiments, because often what you know may not be so. And so that's why we do the experiments. So now we know that the sliding friction does not depend upon the surface area.
All right, got it now? Can you remember now? Does it depend now? No, it doesn't depend for the same object. Experiment show the physics also get you some sort of idea. It won't depend. All right. So it's the first point I want to make today is the friction. It doesn't depend. Now this graph, how to understand, is like this. You try to increase the forces. Now, when you start from 0, the forces, if this is 0, the force to the right, of course, there's no friction. So there's 0, 0. Now, when you increase to 1, this is force increase to 1. If this one is not moving, what's your conclusion? What's the friction? 1. Increase to 2, 2. So as long as this object is not moving, how much force you push this block to the right-hand side will be balanced by the friction. So the friction growth depends on the force applied before it moves. All right. Let's look at what happened. Once it reached this one, suddenly you find the friction reached the maximum and it start moving. Once it start moving, this is what happened. You will find no matter how you push, say, for example, this is your critical is 5 Newton. You put 6 Newton, what happened? Your friction still, say, 5 Newton, or 4.5 actually, 4.5 Newton to here. So how about you increase 7, it's still 4.5. 8, it's still 4.5. It means the friction reaches a constant. Can you see it? So this is how this graph shows you. The friction increases when you increase the force until which now this maximum value is slightly bigger than the constant value. The friction will remains. Now, it's complicated. Mechanical engineer, some of the mechanical engineers spend a whole time in studying friction. Why? Because they want to reduce the friction between the machine. A lot of energy actually wastes during the friction, the gear. If you can have a material which removes slightly 10% of the friction, it will reduce a lot of energy lost. Can you see? Therefore, it's a special area called tribology. Tribology. If you Google this one, now you will see this is the area people study friction, all right, especially for mechanical engineering. You need a lot of material science, chemistry, and in order to find out, some even put some particle inside. Why? Because so hot, when they try to improve those thermal conductivity, so your heat can be dissipated. Otherwise, you can imagine if the two parts of the machine, they're in contact, because the friction, it generates so much heat, it can melt the material, and then you can damage the machine. Therefore, removing the heat from the friction during the friction is one of the most important parts studying in mechanical engine. All right. Now, therefore, we have first look at this number. This is your maximum. I say again, this is your maximum. It means before it reaches this one, friction is proportional to the force you apply. Whereas the maximum, how to calculate the maximum? Is say the friction either smaller or bigger than this number. This is a normal reaction. This is the coefficient of static. This is materials dependence. It depends on what materials between the two surfaces. Whereas kinetic, we see once your object starts moving, the friction is reduced a little bit. So therefore, this number also reduces. Now, there's one important thing about these two numbers. Remember again, static coefficient is always bigger than this one. So mu s always bigger than mu k for the same surfaces, the two surfaces. Friction force or friction, yes. If you apply the force here, this one and this one, it depends on this one. You see, therefore, this one, F static, the maximum is static normal force. Once this one's moving, this one is now the kinetic one is always constant with this one. That's how I say the horizontal force, the friction, depends on the vertical component. Got it? Now, as I say, friction is important. Without friction, you can't walk. So remember, last week we see when you walk, your feet press downward to the ground. The ground pulls you. This pulls you is due to the friction. If no friction, you cannot produce enough force to push you forward. Therefore, all the tire, if you look at Formula One, when they start the racing, do you notice what happened to Formula One? When before they really start, they have a warm-up lap. Exactly. They want to make their tire hot. Therefore, they sort of melt, not fully melt, of course. They calculated how much temperature. They sort of increase a little bit melt of the sort of rubber with the roll. So roll is very rough. So if you can melt a little bit, you produce more friction. So you say, why they need friction? Later you will know. When you take the curve, you take a turn. When the car turning, it's interesting. When the car turns, it's the friction along here produce the centripetal force. So the more of the friction, the more centripetal force it can produce. It means you can make a sharper turn and faster. So it's all physics there. You see the spoiler on the car. The spoiler, the car, the shape is opposite the shape of an aircraft wing. Why? The aircraft wing want to get the aircraft what? Up. The spoiler of the car want to get the car down. Got it? Because why? Because more normal force, you get higher friction. The friction will give you a better, larger maximum centripetal force you can use. And then you can make a faster turn and a sharper turn. So this is all physics behind all these everyday engineering phenomena. So friction is a friend. Go here. Now let's look at these first examples about friction. How to stop a car. Now let's look at this example. You have a kinetic, you have a static friction, and there are tires, and the dry road is here. To be honest, I mean, remember last few weeks, it was pretty wet, Sydney, and my car actually slippery. And when I took it to the mechanic, they just say because the tire is not the best tire. So under the water, it will just, the thing is, when you're a tire, especially you lose the thread, the pitch. The design of the tire is let the water go out and remain in contact. If you lose the thread, what it means, the water will build up between your tire and the water nowhere to go. And then your friction now is not determined by the tire and the ground. It's determined by a layer of water. What happened? Reduce. Because you got the water in between. Can you see it? So that's why your tire, the enough thread is important. If the depth is not enough, it's actually against the law, you know. So it's dangerous. And let's look at here. This is your kinetic. It means mu k is 0.61. Mu static is 0.89. You see, it makes sense. This static always bigger than the kinetic. This is for not moving. This is for moving. Now, if the car is traveling at this one, you already calculate. Remember how to calculate? From 90 km per hour to meter per second. How do you calculate? 90 over 3.6 is the conversion. If you were in the boot camp, you remember. And determine the minimum stopping distance. Now, this is good. You see, if the stopping distance is different, it makes a huge difference. Now let's look at it. We look at F equal to ma first. F equal to ma. Now we first look at what's the acceleration. What it means, this problem is, now this is a good illustration. Now your car is moving to this direction, agree? Now it suddenly stops your engine. For example, you don't brake it. Your car will still move and eventually stop because of friction. Now let's look at the language, get the language right. Remember, I always say, when the car stops here, it's slowing down, you can use this term, what? Deceleration. So whenever it's slowing down, it means the acceleration is opposite. Remember this rule? I always play this one. When this pen goes up, where's the acceleration? Down. And you see when the opposite, the motion opposite the acceleration is slow down. Can you see it? The same when you apply this way. Got it? So when your car slows down, it means the acceleration which way? This way. Can you get that? Yeah, always opposite to the where it's slowing down. Exactly, just vertical. It slow down, during it up, the acceleration is down. So you just turn this one. Once you the acceleration here, you know what is the force now? The force has to be here, parallel to the acceleration. What's the name of the force? Friction. Now you first know the acceleration. So acceleration, therefore, you go back to here. You say what is the acceleration? I know the acceleration if this car move to here, stop already, so you got the initial velocity, but there's no engine. You already cut off from the engine. There's only one force, which is friction. So this force produces an acceleration along the force. Because it moves opposite to the acceleration, the car will slow down and stop, of course. Now, this force is friction, so the friction have to rewrite as what? Proportional to mu and normal reaction. And this is MA. Now, the interesting about here, normal reaction is equal to what? mg. So the both m cancel. What you get is A is actually, now the A here, you have to be careful this time, is the sign. When you put F here, from here to here, you have to put a negative y, because now you know the force is a negative to the left-hand side. So it's a negative. You're moving in the positive direction. So the force is always, against the acceleration, or parallel to the acceleration, but in this coordinate system, it's negative. So therefore, your A is negative here, and G. So it's a modify your 9.8 by a number. Which number is smaller than 1? Now, we start from here. Go back to some of our kinematic. So it's easy now. We can apply the same equation. We know now this is your force, this is your initial, this is your final equal to 0. Initial is where you cut the engine off. And I know now the force, the A, is negative mu g. Therefore, I use this one. You want to find the distance. We arrange your equation. Can you see it? Plug the V equal to 0. Makes sense because now you want the car stop. You want to know this distance. And the A is negative. It makes sense again because, as I say, the A, you measure here positive, the A is negative. So interesting, again, these two negative canceled out each other. And you got u squared and 2 mu g. Plug your number in now. Remember, you have two numbers. One is static. One is what? Kinetic. What is the static? The static one is 0.89. Kinetic is 0.61. So if you use static, 35.8. Yep. If you use kinetic, 56.3, which is shorter, static. Makes sense? Because static coefficient is higher. So if you substitute this one, this with the static coefficient, you stop here, kinetic will move farther. The problem is what coefficient we should use for the real car, static or kinetic? Think about it. Kinetic, yes, because the car is moving. No. No. Think about which coefficient you should use for the real car, static or kinetic. I say again, it's not kinetic. You must use static. Now, I'm going to show you that the two, because the cars, now this is again critical. Now attention please. Shh. Now attention please, this is critical about understand why you should use static coefficient, not kinetic. You see the car is moving against your intuition. Let's look at it. When the car in contact of the road, this is the wheel. I call this rolling, can you see it? Now if this is not rolling, sliding, can you see the difference? Now, when the wheel is rolling, I use static coefficient. When the car is sliding, okay, it means it loses traction. It loses traction because the ring. Just what happened 3 weeks ago, my car. This you use kinetic. Now, You may ask why the wheel is rotating. Yes, there's a trick here about the contact point. Now, I won't persuade you or prove in here. It will be in next week. Now, you remember at this stage first, when the tire has gripped the road, when it's really rolling, the contact point actually is not moving. The velocity, the moment of velocity is 0. Because think, the contact point here is this way, but your car is moving this way. They are just about cancel out each other. So the contact point, the momentum is 0, the velocity. Therefore, you use static. Now, it's very tricky, this concept. It's not easy. However, you can imagine, once it's sliding, lose traction, it's like a sliding now. Therefore, think about why sliding, skidding, is bad. Because you lose traction. See what happens, the stopping coefficient. It takes a lot longer to stop your car, makes sense now? Therefore, the safety. Now, therefore, again, driving on the wet condition is extremely dangerous, especially you try to push your pedal. It may cross sliding. Once it's sliding, your car will lose traction. It means you cannot grip your surface, and then you will have a longer distance to stop. It means when you brake it, it's a lot dangerous to stop your car. Get the idea? And that is the physics behind it. Now, as I say, I'm not going at this point the detail why when the car is gripped. There's a lot of physics in car, in all this. Frictional force steering. Look at another example here. What's happening? I think okay, did I show you this one before? No? Yes? Okay, sorry, yeah. So, I don't know, somehow we swapped it. All right, frictional force steering. That's what happened. Remember, I say, when your car turn, say again here, when your car make a turn here, it is the friction this time is not here. Yeah, there's a friction, but the most important, they develop another friction here. So when the car turn, it's the friction here provide the centripetal force. Remember, I say centripetal force is not a new force. It is how to use a proper force, say gravity, friction, tension, function, act as like a centripetal force. So centripetal force is a function. It's just like a profession. Same person, it can be a profession here, it can be a different role. Centripetal force is one of the role a force can take, which you can keep a object rotating. Now, look at here. If the car in here is facing to you, like here, try to turn, from your point of view, try to turn this way, all right? There's a friction produced here. There's a normal reaction that's here. So F equal to ma, yep, you have a friction now. The A, this time, you must replace to V squared over R. Now, we haven't touched this point yet. We'll come back next week. So the acceleration, because you're making a turn, so this R is the radius of the turn, okay? The velocity is, yes, of course, the velocity. Now, the N, of course, is mg. You plug this one, you see again, the M disappear. It's very interesting. It doesn't matter how heavy you are, your car. As long as there's the same static coefficient, it will have the same physics. So what you get is, if you get here, mu g equal to V squared over R, and then you turn this one back to here. This is your velocity. What it means, it means when you make a turn, the velocity you are allowed to make this turn, the maximum velocity, is square root coefficient of friction between your tire and the ground, G, and R. Now, can you see this is what I say? why the Formula One want a higher friction. Can you see it? The higher the friction, what is the velocity will be higher. It means you can go into the turn with a higher speed. That's the advantage. More friction. Higher speed, yeah, you can turn it in a higher speed. So it's against your intuition, of course. Because don't worry about the heat, the energy, the power the engine will supply. It's not the engine I'm talking about, it's the physics, whether you can make your car make a turn at a fast speed. And this, you see, is related to what? To the frictional coefficient. And of course, the R, the longer, the bigger the R, the larger the radius turn, of course, is faster you can turn. It makes sense again. Now, what happened? What happened again? If you're making a turn, this is an important exercise. We go back to this here. If you're making a turn with V, given by here. Now, if this is your maximum V, you can enter this row. Okay? This is your row here. And this is your R. Now, what happened if I make a better drawing? Yep, this is your road. This is your car here. So how to make the R? You measure here, like you draw the complex. This is R. Got it? So this is your V, the maximum. So you make a turn. Now my question is, if you try to enter this one with a velocity higher than your maximum given by here, higher than this one, what happened? It won't skid. You still enter, but you look at the physics now. It's the physics. If your V is higher than this one, what it means, you cannot change this one. You cannot change this one, but the nature will force you to change what? This one. So for example, instead in the maximum calculation, you decide this R is 10 meters. If this velocity is higher than what it designed, this row, you will force this one up to what? Say 12 meters. Make sense now? Because the V larger, this must be larger. Think about what happens. If the row is designed 10 meters, if you enter with higher speed, you have to turn at 12 meters. Your car will go which way?
More to right.
Like this?
Yeah.
Now, if this is your cliff, you die. Of course, you crash. Can you see when you enter a turn with the speed higher than design limit? You remember when you turn every turn, there's a road size say what's the maximum. If you try to beat the physics, now who's designed this speed? You know who's engineering doing it. Which professional will do this, design all this? Is civil? No, it's civil. Interesting, yeah. Civil engineering do this. If you can find a job in marine, in road department, and build. When you design the road, think about your civil engineer. You design the road, you have to have a physics, and design the turn. Got it? And this is where you apply your physics knowledge to make your limitation. What is the limitation for the car to go into the rain? Otherwise, you crash. And remember, you cannot beat the law. Some of you say, how about I steer by steering? You know what happens? You lose control. And the most important, lose traction. So your rear tire will lose. You got a stung like the cartoon in animation. Is it called I forgot the name of the animation. Initial D, yeah. You can do a stunt turn like this and doing like this. But you don't want to do it in a row. Why not? Because you're not skillful. You're not the most.
So we need to learn physics in order to drive a car.
Well, yes. Driving a car, you see, you all did physics. Once you learn this class and this particular lecture, you know there's a lot of physics in driving a car. Yeah, you will become a mechanical engineer, civil engineer. If you want to become an electrical electronic, you still find a job in the car industry. Why? Tesla. Tesla is all about a motor. There's a low engine. There's a 4 motor connect to the wheel. So you start, you just connect, you just like a press a button, and the motor just start. And the experience, I was told, someone sit in a Tesla, he say, the driving, the sitting experience as a passenger is totally different. You will get the acceleration you will never dream of because the very different physics inside involved in an electric car. All right. See again now, as I say, this is important formula. Never try to beat the physics, otherwise you pay a heavy price. You go to hospital or you die. Got it? Once you know the physics, you will really respect the nature. You say, well, I'm different, I can do it. No, you can't, because we're all subject to the physics. All right, a level road, it make a 90-degree turn. What it mean 90-degree turn? Now you see, you can design the road like this. A small turn. This R is very small. Can you see it? You can make the same 90-degree turn with like here. You still turn 90 degrees, but this time, this is a lot bigger. Now, when you do a civil engineering, which one is you should use? There's so many factors. Of course, if you have a free land, you can design whatever you like. But if you have designed a road in an established area, you don't want to design this one, you have to design a shorter turn. Therefore, the limit will be very limited. The speed you allow a car. Makes sense now? And it's all about, now, the rate is 73 meters. What's the maximum speed? When the road is dry, you can use this one. And the road is wet. You have to receive. When the wet is coming from 0.88 to 0.21, it substantially reduce the coefficient of friction. Can you see it? Now let's do it. You plug the numbers again. You see when this is dry, your velocity, maximum velocity is 25 meters per second. When it's wet, it's 12. Can you convert this one into kilometer per hour? Yes. You multiply what? 3.6. So you multiply. What was about multiply 3.6 will give you? So 25, 3.6, 90. So you're doing 90 kilometers per hour. If 12 multiply 3.6, 43.2 kilometers per hour. Now what it means, for the same tire, same road, because the coefficient is different. When it's snow, when it's dry, your maximum for the same turn is 90 kilometers per hour. When it's wet or snow, it reduces it to 43.2. That's important. Can you see it? Substantially less when you are driving in a snow or wet condition. Now, driving a trunk, same. Now, experience tell you, if there's a box here, you want to drag it this way. Do you want to push it this way? No, because you see the difference. When you try to get a force here versus when you try to push from here, which one is more clever way to do it?
The left one. The first one.
The first one. Why? Because now, which one have the same mg, the same mass, but you see, when you push this way, there's a component of this force. Can you see it? This is y component. So overall, your normal reaction will be reduced.
Yes.
When you push this one down, you add the normal reaction down, so your friction increases. Can you see it? Therefore, it's more natural for people to drag things across a rough surface. rather than you push it down. Again, it makes sense. And you see this is how they analyze. You have a t, this is a t sine theta, the normal direction, there's a t cosine theta. And now, the normal reaction, what it means is t sine theta at the normal reaction equal to mg. So the normal reaction will be mg minus t sine theta. So it's a less than mg. So first of all, remember the friction is equal to normal reaction. It's not mg. It's how much the normal surface react. So reduce the reaction, you reduce the friction. So I may not go here. That's it. We actually finished earlier, so we can now have a look at your laboratory, your P-lab, all right? Wait a second, I need to upload the can you wait 1 minute before I look at the lab, because I have to I forgot upload the lab manual. All right. Sorry. Okay, here we are. This is your this week's laboratory. Now let's look at the setup first. Look at the setup. this is your setup. Now, you're going to build. We already give you a track. Okay. All right, look at. Now you have a track here. You put a. You put a ball here. Now this ball will, of course, now you calculate this one is h from here to here. Now we will spread from here. I'll say again, we spread from here. You got potential energy, agree? Now the potential energy you see within this is mgh. Now when your ball loses your potential energy here, it will go this way. So this you got a velocity u. This is your kinetic energy. So here you can use mgh equal to half mv squared, but it's not simple as this. You can say, all right, I remove this 2, and I will get v equal to square root 2gh. Actually, there's one thing you will miss in this simple argument you learned in high school. Now, what you find is you should use this expression instead. So instead of square root 2gh, you use 10gh over 9. This is something you want to find out. So you got the h, you got the g. Now, once you got the h and the g, if you go back here, this is your trajectory. This is your path, which your ball dropped to here. From here to here, this is your x. From here to here, this is your y. Now, if you look at what the theory say the x is horizontal direction, as you always know, multiplied time, whereas the vertical component, you can use either of these. Now, but if you really want to relate the x and y, you may want to say this may be a better choice because this is time in, this is a, now this equation just like here, v equal to plus 2as. It's just like this, but this time you use it in a vertical sense and your s become your y. Can you see it? And your initial is 0. So therefore, v squared equal to 2ay. So it's nothing mystery. It's just the same equation you've been using in the different contexts. You use this one, and you use x equal to v. Now this is vy. This is vxt. Another possibility is you can use this one. I beg your pardon. The second one could be even better. So I beg your pardon. So you will use x equal to vxt, and the second one y equal to the half gt squared. Now, what it means, you substitute the t. So it means you remove the t, elimination the t. If you have an equation like this, you eliminate the t, what you will get? You will get x and y. So what you can do is from here, t equal to x over vx, t squared is this square. And then you say y is equal to half g x over vx squared. Can you see it? And you can rearrange this one. You will rearrange this one until you have a form which is x equal to a k equal to y. So the k will be all about half g v what square all this number. Can you see it? You just rearrange your equation from here to here. This is your part A of your P-Lab question. Can you see it now? So part A is not hard. All you need is substitution. And from here, you want to find what is k in this expression. I already done half for you, so it's 5 marks. Now, this part is a little bit hard. So I will sort of work out what to do. Now, if you have later, when you're dealing with uncertainty, you're going to deal with, you measure x, but you need x squared. So how to do it? You first let z equal to x squared. You want to know is what is delta z over z. Now, if you want to know what is delta z over z, all you need to do is now is look at here. If this is a z, this is x squared. Your delta z will be 2x because z, you have 2x delta x over x squared. Can you follow the mathematics? A bit of calculus here this time. Can you follow the mathematics?
Yes, yes.
How can I explain to you? I'm not a mathematician, so usually when you z equal to x squared, delta z is equal to, just like take derivative, 2x. Okay, get it like this. Delta z, delta x equal to what? 2x, agree? Yes. So you rearrange. I know how to do a math now. Delta x, can you see it now? You use the delta x multiply back here. Now, I know in true mathematics you are not allowed, but in physics you are allowed. You are allowed to treat delta x as a denominator, just like a number. So can you see it now? So once you substitute here, z is here. So from here to here, you should be comfortable now. You use this one. Now, once you got this one, you see, you cancel this one. So it's a 2 delta x over x. So it means this is what you and this is not finished yet. Delta z over z, this is. So delta z is equal to 2 delta x over x multiplied z, and z, what is the z? X squared. So this is 2x delta x. This is this one. Now again, this is a bit of math. Therefore, I work it out for you guys. If you watch this video, you got the 5 marks. If you still don't like to watch my video, sorry, you have to work it out, and most likely you won't be able to work it out. Sorry?
Can you scroll up a bit? The previous question.
The previous question. I already pretty much done this one. Yeah. So I already sort of show you how to do the pre-lab. As I say, I will use the Monday lecture at the end of 10 minutes to show you the week. Of course, next week you're going to have a skills test. I won't show you the skills test answer. I won't.
Sir, could you?
Yep. Remember, I will upload this video this afternoon. You can always watch it again and ask your friends to watch it again. So everybody's fair. If they don't watch it, I cannot help. And you come here, so therefore you listen live.
How come?
All right, I think I have to stop here and hope to help you at least. There's a bit of math you may not be comfortable with. Yeah.
Just the delta 8 has a value?
Yes, the delta x is later when you do the measurement of the x, the uncertainty. Yeah. So you have to do the uncertainty, and this is your value of x, and then you got the delta x square uncertainty. Later, when you do the math later, when you look at the question in the lab, you will know you need to use this expression. You need to